Hi, welcome to the video on Archimedes Lab. You're going to watch this video to enable yourself to complete the lab. So let's get started. In the previous video, we talked about different types of properties. So properties can be classified as physical and intensive. Physical meaning that you can observe it without changing, and intensive meaning that it's inherent to the substance, and independent of amount. It can also be physical and extensive. Again, physical, you can observe it without changing, and extensive means it depends on the amount of substance you have. And here are some examples for each type. Finally, we have chemical properties, which means you observe it through change or chemical reaction. And so you can have a chemical intensive, so you observe it with change, it's independent of amount or intrinsic, or you can have a chemical extensive property, one that you observe it with change, but it's dependent on the amount. Now, in the early part of this unit, I did a demo where I turned a penny into a gold coin, quote unquote. And many of you guys didn't believe me that I did that, right? So if you were to test the gold coin, I want you to choose a property that you could use to test a gold coin without destroying it. So pause the video now. Which one of these properties would you use to test, or which type of property would you use to test a gold coin? So if you don't want to destroy the gold coin, you definitely want to go for physical and intensive. So physical, you can observe it without changing or destroying it. And intensive, you would want to go with that because it's inherent to the substance. So that means no matter how many coins I have, that property will remain inherent to the gold coin, the penny, or whatever. So this leads us to the legend of Archimedes, who had a sort of a similar dilemma. There's a legend that states that a king wanted to see whether or not he was given a fake gold crown, and so he asked Archimedes to come up with a way of testing it without destroying it. And Archimedes decided to test, or determined that he could test whether the gold crown was real gold or fake gold by measuring its density. And so he did this famous experiment, and of course this is actually probably not true, it's probably a legend, but it is very in keeping in what we're trying to do, which is test the gold coins to see if they're real gold without destroying them. So in this lab, you're going to use density to determine, the density of real gold, regular pennies, and the gold coins that I made. And then you're going to compare the density of the gold coins to that of real gold and regular pennies. And you're going to use the density as evidence to write a CER whether or not I turned the penny into gold. So let's talk about what density is, because we're mentioning that's what we're going to be using, so we should kind of have a sense of what it is. Density measures the compactness of a substance, and the equation for density is mass divided by volume. So denser substances are more compact. That means the particles are closer together. So if we look at substance A versus substance B, we can see that substance A is denser because the particles are much closer together than in substance B. Now, because the particles in substance A are much closer together, if you have the same size of substance A and substance B, you're going to be able to pack in a lot more particles into substance A. So which one do you think will weigh more, substance A or substance B? Right, it's substance A because you have a lot more particles in it. All right, so now that we're talking about density, let's see if you can arrange in order of increasing density wood, styrofoam, and steel. So since we're doing increasing density, the first substance that you write will be the lowest density, and then the last substance you write would have the highest density. Pause the video now. When you press play again, the answer will be revealed. All right, so styrofoam is the least dense, then it's wood, and then it's steel. Let's take a look at the particles to see how this relates to our understanding of density and compactness. So if you look at a close-up of styrofoam, you see the gray sections are all just empty space. So there's a lot of spaces between the particles that make up styrofoam. With wood, when you zoom in, there are empty spaces. In fact, there are some larger holes and some smaller holes as well, but the particles are packed more closely. And in steel, in this image with this type of microscope, you don't see any spaces. Now these white portions are just light reflecting off the steel, but there are no spaces in between. So steel is the most compact and the most dense, and styrofoam is the least compact and the least dense. Now, which one do you think would weigh more? Let's say you have a 65 centimeter cube piece of wood or steel. Which one would weigh more? So just to pause for a second, 65 centimeter cube, that's the volume. And I know this is the volume because the unit is centimeter cube. So just keep that in mind, that that's the volume. It basically shows the size of the wood. And which of these will, the size of the wood and steel. So which one will weigh more? Pause the video now, and when you press play again, the answer will be revealed. Great, the answer would be steel, because steel is more dense or more compact. You can fit a lot more mass in that same amount of volume or space. All right, with density, it's important to note the units. So the units of density must match the units for the mass and volume from which that make up density. So in this table here, you see the first row has density, next row is mass and volume, and then if we go down each column, we'll see units that sort of match up. So let's take, for example, the first one. The top unit, G, grams, is a unit of mass. And the bottom unit, centimeter cube, is your unit for volume. So if your density is reported in grams per centimeter cube, that must mean your mass is in grams. So the top unit tells you the mass the top unit in density tells you the unit for mass. And your volume is in centimeter cube. So the bottom unit in density tells you the unit for volume. Similarly, if you look over here at this second column, density is in grams per milliliter, and the top unit again is grams, so that tells you the unit for mass, and the bottom unit is the milliliter, and that tells you the unit for volume. So the key thing is you have to make sure that it matches up. So likewise, but on the flip side, let's say you are given the mass in kilograms and the volume in liters, and you use that to calculate or determine the density. That means your density must be in kilograms per liter. So the top unit is it comes from your mass, and the bottom unit comes from your volume. Now, how is density helpful here? You're going to use density to help identify a substance. So because density is an intrinsic property, it can be used as evidence to support or confirm the identity of a substance. Sorry, there was a typo there. So going back to this, density is an intrinsic property, and it can be used as evidence to support but not confirm the identity of a substance. And we'll see that in a moment. It can be useful, however, for ruling out substances. So let's say, for example, you have three substances, A, B, and C, and the density of A matches that of B. Notice how the densities are pretty close, but it doesn't match that for C. Okay, now another typo there. Sorry, guys. So now it doesn't match that for C. So looking at these densities, we can say that substance A and substance B, we can say that substance A is not substance C. And we can say that substance A could be substance B, but we can't say it's definitely substance B. So really what we can use density for is ruling things out more and sort of using it as partial evidence to identify a substance. Now, to know for sure whether A and B are the same thing, you would have to test other properties. All right, let's try the CFU. An unknown rock has a density of 2.7 grams per milliliter. Could this rock be shale? Explain. If not shale, what type of rock could this be? So here we have a table of different types of rocks, and the densities are on the last column. And we want to know if this rock, which has a density of 2.7 grams, could it be shale? And explain how we know. And if it's not shale, what else could it be? So go ahead and pause the video now, and when you press play again, the answer will be revealed. So this rock cannot be shale because the density of shale is 1.6 grams per milliliter, and the density of the rock is 2.7, so they don't match, so this cannot be shale. However, it could be quartzite or sandstone because they have the same densities, but we don't know for sure if it is quartzite or sandstone. We would have to test it further. Now, how do we measure the density? So in this lab, you're going to be measuring density. To measure the density, you need the mass, you need the volume, and then you use the density equals mass over volume equation to calculate the density. So in this example here for the data table, you notice how they have a column for mass, a column for volume, and a column for density. All of these values for density was calculated by dividing the mass by the volume. So for example here, for sandstone, the density is 2.7 grams per milliliter. We get that by dividing 54 grams by 20 milliliters. So let's take a look at these measurements that we're talking about. We said to get density, you need the mass and the volume. So how do we measure mass? For mass, you're going to use an electronic balance. And here are just some sort of things to point out about electronic balance. I'm not really going to go into them because since we're doing things virtually, we're not really using electronic balance, but this is what it's called. You can also use a triple beam balance, which is a non-digital way of measuring. That's the one where you sort of move the little, scales over, I forget what they're called, in order so that the balance balances out, and then when it balances, it tells you the weight. But we would use an electronic balance in this lab to measure the mass. And all you do is you just place the substance on top of the that's called a balance pan, and the mass would read in the digital window. Now, one thing that is kind of important to know is when we get back into the labs, electronic balances and hot plates look similar just from the shape, but they're not the same thing. So for an electronic balance, they have buttons and a round top, and a hot plate, which is used to heat things up, will have dials and a square top. So they look the same, but they're not. All right, we talked about measuring the mass, so let's talk about measuring the volume. There are two ways to measure it. The first way is the geometric formula, and that's what you've done since you were in elementary school. So you take a ruler and you measure the lengths of the sides of an object. And this method, and then you plug it into the volume equation based on the type of object you have. This method is useful when you have a structure that has straight and regular sides, but it's not so useful when you have something that is irregularly shaped, like a gold nugget. In which case, you're going to move over to the second type, which is water displacement. So in water displacement, you fill up what's called a graduated cylinder to a certain volume, so you fill it up with water. That'll be your initial volume, or VI, and you record that volume. So in this case, the water was 17.1 milliliters. The volume of the water was 17.1 milliliters. Then you add the object to that graduated cylinder, and you notice the volume will increase. And it will increase by the volume of the object you just add. So by taking the difference between the initial and the final volume of the water reading, you'll get the volume of your object. All right, let's see which methods we would use for each one. So we have a cell phone here. If you wanted to measure the volume of your cell phone, would you use water displacement or the geometric formula? Yeah, you're probably going to go for geometric formula because you don't want to get your phone wet. And the sides of a phone are pretty regular and straight, so this should be sufficient. All right, what about a rock? Which method would you use? Yep, you would use water displacement because you can't really measure this rock since doesn't have regular straight sides. So you can't measure it with a ruler, but you can use water displacement. What about a gold coin? That's right, you're going to use water displacement. So in Archimedes Lab, where you are going to be measuring the mass and the volume of gold coins that I made to see if it's real gold or fake gold, you are going to be using water displacement. So let's take a closer look at how we utilize this tool called a graduated cylinder. First thing, we have to choose the right tool. Oftentimes people choose a beaker rather than a graduated cylinder. A beaker is sort of short and it has fewer lines measuring the volume. And a beaker is not doesn't give an accurate measurement or precise measurement for the volume. So you don't want to use it for that. Beakers are used to store and hold things. For a graduated cylinder, it's a taller, longer piece of glassware, and you'll see that there are more lines on the graduated cylinder. So if we're in an actual lab, it's important that you choose the right equipment. All right, so how do you measure the volume? You need to be accurate and precise. So let's start with being accurate. When liquid is placed, certain liquid is placed in a graduated cylinder, it forms this curve called a meniscus, so this curve. And with water, it curves down. Now, some liquids actually curve up and some are sort of like flat. But since we're going to be using water, we're going to look at the one where it curves down. Now, what you want to do is, in order to be accurate, is to level your eye at the meniscus, at the bottom of the meniscus. So you would lower yourself until your eye is at the bottom of the meniscus. And that's a bit tricky, and you kind of have to get used to doing it. But once your eye is level, then you're going to get an accurate reading. The other thing is you want to read the bottom of the meniscus. So you don't want to read up here at the top of the curve. You want to read at the very bottom of the curve. Now let's move over to how do you be precise. Well, in being precise, it really has to do with how you're reporting your values. Here we see the meniscus is between, this is the 35 mark, so it's between 36 and 37. So we would read this as 36.5. Now I'm being precise here because I'm estimating that last digit. Maybe someone else would read that as 36.4, or someone else would read that as 36.6. That last digit is your uncertain digit, and it's important that you estimate it. What would be a non-precise measurement is 37 milliliters if someone, let's say, just rounded it up. So that would be incorrect because you did not estimate the last digit. Let's take a look at some CFUs. So I want you to report the volume accurately and precisely. Pause the video now. When you press play again, the answer will be revealed. Okay, so the answer here is 67.0 milliliters. Now, some people may just have said, oh, it's 67. That's incorrect because it is not precise. Remember, even if the last digit you believe is 0, you believe that the meniscus, bottom of the meniscus is exactly on the 67, then you have to put the 0.0 there. All right, report this volume accurately and precisely. Pause the video when you press play again, the answer will be revealed. So in this case, I have 43.0 milliliters. Now, perhaps you reported it as 39.9 or 40.1. All of those readings, remember, are acceptable because that last digit, your uncertain digit, is sort of an estimate, right? You're the one sort of guessing it. So everyone may have it, may do it differently. And so that's totally fine because it is the uncertain digit. But the key thing here is make sure that you estimate that last digit, that last number in your volume reading. Okay, now that we've gone over the types of measurements and equipment that we use for mass and volume, let's go back to density. So we have a few CFUs, see if you remember how to calculate density. So in each of these examples, I'm going to give you information about the mass and the volume. I want you to calculate the density with the correct units. Pause the video now. When you press play again, the answer will be revealed. Okay, and here is the answer. So the mass was 122.7 grams. The volume was 20.0 centimeters squared. So you just divide the mass by the volume, and that gives you the density. Let's try that with this CFU. So we have the mass of a liquid and its volume as well. Pause the video now. When you press play again, the answer will be revealed. All right, the answer here is 5.54. Now, if you got a different value, like a value less than 1, you probably divided the volume by the mass. You probably did 8.54 divided by 47.34. So how could you avoid that error? Use your units. The 47.34 grams tells you that that's mass. So you're going to divide 47.34 by 8.54. All right. All right, here's a quick summary of what we looked at so far. So density measures compactness. The equation is mass over volume. When identifying an unknown substance, you can use the density to rule out a substance if the densities don't match, or suggest what substance the unknown can be, but you can't confirm it. Now, to measure the density of a substance, you need to find its mass, which we use a balance for, or its volume, which you can either use a geometric method or a water displacement method, depending on the substance you have. And then you would just calculate it using that equation, density equals mass divided by volume. All right, so let's go into the lab now. So remember the lab, you're going to determine the densities of gold, regular penny, gold coins, and then compare, and then use it as evidence for your CER. So what would the procedure look like if you were in the lab? Well, first thing is you need to get the densities of all three substances, a gold coin, regular penny, and real gold, regular penny, and the gold coins. So let's start with the real gold. If you had a gold nugget, then you would first weigh it on an electronic balance and record the mass. Then you would fill about 25 milliliter graduated cylinder with a approximately 15 milliliters of water, add the gold nugget, and record the final volume. So you need the initial and final volume for that. The pennies, you would do something similar, except for you would use a 50 milliliter graduated cylinder and fill it to approximately 30 milliliters of water, and record your initial and final volumes and your mass. And then you repeat that for the gold coins and then calculate the volumes and densities. So let's see what that would actually look like. So here we have our gold nugget, and if we put it on an electronic balance, we get a mass of 114 grams. So the first thing I'm going to do is report in my data table here, the mass is 114 grams. All right, the next two columns of my data table have the volume of water and then the volume of the water and real gold. So that's my VI and my VF. So in the image here, we see the initial volume of the water is 17.1 milliliters, so I fill that in here. Then after I added the gold nugget to the graduated cylinder with the water in it, the volume rose to 23.0 milliliters, and so I would fill that here. Now the last two columns, you actually have to calculate. So let's start with calculating the volume of real gold. This is water displacement, so what you need to do is subtract the two, take the difference between the two volumes. So in this case, we would do 23.0 minus 17.1, and we get a volume of 5.9 milliliters. And lastly, to get the density, it's mass divided by volume. So we would take the mass from over here, 114, and divide it by the volume, 5.9. And that gives us a density of 19 grams per milliliter. Now notice that I have the units. That's important. Do not forget the units here. So they're grams per milliliter. All right, so now you're going to do the same thing. So that first table is filled out for you in your lab. All right, so going to your lab now. This second table is only partially filled out, or is not filled out for you, so you have to fill this out yourself. Now this is the data for a regular penny. So here we have the image of the electronic balance. This is the mass in grams. Here we have the volume of the water by itself, and then the volume of the water with the gold coins. Now one thing I will do to sort of help you out here is because the volume of the water, I want you to be clear about what the bottom of the meniscus is. You see how it's slightly curved? And there's sort of like a double line there. There's like this really thick blue line. You want to be at the very bottom of the meniscus. So the very bottom of it in the middle there. And not the bottom of the top line, but like very, very bottom, okay? So that's where you're going to be reading from, all right? And of course, that initial volume will go here. And then the volume of the, I wanted to actually show you what I got for that. So when reading the bottom of the meniscus, I'll go back. So this is the 34 line. The longer lines are, go by 1 milliliter. And then the little short lines that are in the middle, you can just ignore those. Those are half milliliters. And then this really long line is 35, okay? So this is 34, this is 35. And the bottom of my meniscus is here. It's closer to the 34 than it is to the 35 milliliter mark. And so I estimated that to be 34.3 milliliters. Maybe you got something slightly different, but I'm reading the very bottom of the meniscus. So you want to add this value to your lab, to your data. Okay, so then you'll also have in your data the volume with the regular pennies added. So that's in here, and you would read this. So here the line is, this is the 39 mark, this is the 38 mark. That would make this a 37 mark. Where do you think the bottom of the meniscus is based on that? And you fill this in here, and then use that to calculate the volume of the pennies and then the density of the pennies. Okay, so now that we've gone over the data for a regular penny, the data for gold coins are here. Again, you would fill in the information based on what you see here in the three images, the mass, the initial volume, and then the volume after the coins were added. And then use that to calculate the volume and the density of the gold. Don't forget your units, and don't forget to estimate the last digit when reporting your volume. So once you have your data tables completed, then you're going to report all your data and show your work for your calculations and answer the post-lab questions and submit it. So that's how you would do that lab report. All right, I hope you found this video helpful. Have a quality day.